So welcome back to another video in our statistics series. So today we're going to be taking a look at data representation, and this chapter is probably one of the easiest chapters out of everything year one stats. And that's probably because a lot of the stuff you're going to take a look at here, you would have touched upon somewhat in your GCSEs. So let's just go straight into it. So what are we going to be taking a look at in this chapter? So in this chapter, we'll be taking a look at how we can figure out what is an outlier and what actually outliers mean. We'll take a look at how you can plot box plots, cumulative frequency diagrams, histograms, and then finally, after learning about all these three different ways of representing your data, we'll look at how you can compare these different data sets together. So going on to the first thing. So the first thing we need to take a look at are what are outliers and what are anomalies. So you've probably heard these words in just like general speak and context, but in stats, they tend to have very specific meaning. So an outlier, if you had to talk about it in general terms, that's usually like an extreme value, and that's not really lying inside the pattern of your overall data. So imagine I had like a bunch of ages, right? Let's say I had let's say I was just checking the heights of different people. So let's say I'd have someone who's 150 centimeters tall, 160, 180. Let's say someone was 170, 150, and so on. And then suddenly I had a value which was like 230. So in general, these values are quite close to each other. But then this one seems particularly larger than the rest. So you can see the biggest difference between all of these numbers, between the large and small, is probably 180, 150 here. So there's only a spread of about 30. But this one over here is much, much larger. So depending on how large this is, if it's too large, then in different cases, you would call this an anomaly. So for example, let's add another one who's 350 instead of 230. Well, in this case, what would end up happening is we'd say, well, this one probably is an anomaly because it's so far from the other piece of data. So essentially that's, and also, yeah, we'd consider that as an outlier basically. So that's essentially what we've got here. Now, sometimes you might have outliers from your data, but it doesn't necessarily mean that it's not part of your data. Sometimes it might genuinely be that you actually have got someone who's 350, but we'll talk a little bit more about that after we've discussed the definition for an outlier. So hopefully that makes sense. So essentially you have a pattern of data, and if something is either too low or too high compared to that data, then you call it an outlier. And sometimes if you consider this data point, which is outside, or this one over here to be wrong, you normally call that an anomaly and you get rid of it. So let's talk about the statistical definition of what an outlier is. So there's different ways you can define it depending on different values, but the way that we do it in stats is usually if you take your third quartile and you add on k lots of the interquartile range, so that's Q3 minus Q1, then anything which is going to be more than that is considered an outlier. And anything is if you take your lower quartile and you take away k lots of the interquartile range, that's also considered an anomaly. So just to explain to you what this looks like on a graph is something like this. So let's say we have a box plot like that. Or before that, actually, let's actually have an even easier example. Let's say I've got a line like that. This is Q3, or this is actually Q1. This is Q3, this is Q2. So what I'm trying to say is that anything which is k times the interquartile range more than Q3 is an anomaly. So I have a tolerance of this much. Anything which is within that is okay, but anything which is more than that would not be good. Same thing from Q1. The only difference is this I'm going down, so we care about minus lots of that. So k Q3 minus Q1 lots. Anything over here is okay, but anything which is beyond that is bad. So basically we have a tolerance level between the two different parts that we have. So anything like that would be considered an outlier. And sometimes, just coming back to what anomalies are, there's sometimes that we find our data has outliers. So let's say this is my data, and I found that this is everything which is fine, and then these are the points, let's say, which happen to classify as outliers. Now, sometimes what happens is that if I were to include these data sets or these data points in my calculations, since they're outliers, they might skew my data or they might give me misleading results. So sometimes your outliers can be considered anomalies, and the ones which you get rid of or data points which make your outcome misleading, they're called anomalies, and you tend to get rid of them. So you wouldn't actually include any of these if you're doing that. But you have to be careful as to what actually is an anomaly, because sometimes outliers are genuine values which could be correct. So, if I was doing heights, there really could be someone who's like 230, let's say. So sometimes you don't want to take it out, and that depends on, kind of experiment you're doing or what you're trying to figure out. That's like one of the questions you have to solve in stats. But in A levels, you won't have to worry about that. They'll usually tell you what's considered an outlier and whether to get rid of it or not. So since we've done all this talking about this equation here, it would probably be a good idea to go through an example of actually how we use this equation. So moving on, let's take a look at our first example. So here we have a set of numbers. So let's see how many numbers we actually have in total first. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers in total. So let's just write that down. We've got 12 numbers. That'll be useful to know. And basically, we're going to be given what the outliers are. And I know that last time we wrote the equation as being k lots of q3 minus q1. The thing is, k will normally be given to you in your A levels. You don't actually have to work out a value of k. So you're normally going to be given that. So let's say we're given the set of numbers, and the definition is that here, your outlier is plus or minus 1.5 times the interquartile range. I'm just using that because that's the same thing as q3 minus q1. I can't even bother to write that out. And from q3 and q1. So it's just basically saying it's these two here. So let's take a look at what our answer should be for this. So how do we start this? Well, the first thing you want to do is you want to figure out what your q3 and q1 values actually are for this one over here. So to do that, we need to figure out how many data points you have in total, which is 12. Great. So let's do q1 first. So we now have 12 data points, and we know to find the lower quartile, divide that by 4, which gives us the third value. So the third value, if you just look along, would be number 5 over here. That's our third value. So that means 5 is our lower quartile. Now let's find the upper quartile. So this will be 12 times 3 divided by 4, which is 36 divided by 4, which is the 9th number. So the 9th number along would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 13. So let's mark that down as our upper quartile. Cool. So now we have our two quartiles. Now, according to our equation, what we said was the outliers were anything which were plus or minus 1.5 times the interquartile range. So let's do that here. For anything to be an outlier from Q1, it has to be 1.5 times the interquartile range, which we know that now. We can write interquartile range as being the 9th number was 13. So interquartile range is 13 minus 5, which gives us 8. So anything which is 1.5 times 8, and then our lower quartile is 1. So we do 5 minus 1.5 times 8, just following from this equation over here. This over here, we found that to be 5. That's given us 1.5, and we just found the interquartile range of this whole thing was 8. So coming back to here, that's what we get. So if we were to solve that, this goes to 5 minus 8 times 1.5 is 12. So our lower quartile gives us a number of minus 7. So if you had any numbers which are minus 7, then those would be, or anything less than minus 7, that would be an outlier. But you can see in this data, we don't actually have anything which is less than minus 7, which is completely fine. That means we have no outliers on the left-hand side over here. Let's try that for the other side, on this upper one over here. So the upper quartile is 13. So 13 plus 1.5 times 8 gives us 13 plus 12, which is 25. So here we can see that nothing is more than 25. So actually there are no outliers in the data set. Everything is fine in this data set according to the definition. Let's say I had randomly added on like a number which is like 48. What I might have ended up doing is it would change your interquartile range and the other values, but probably the value, which is the upper one here, wouldn't be 25. It could have been something like 27 maybe. But then what ends up happening is this number would have fell outside it. So in this case, we have no outliers, but anything which is less than 7 or more than 25 is considered an outlier. And you just have to check if there are any outliers in there. So that's pretty much all you actually have to do for a question like that. So these are quite simple to follow. It's just essentially you've got to find the interquartile range. So before that you have a Q1, find Q3, find the interquartile range, put it into these two equations, get these two numbers, and then you check if anything satisfies that. So is it anything which is less than what it should be or more than what it should be? So that's the first type of question you can get for stuff like this. Now let's take a look at the other type of question you can get. Okay, so for this next question, again, you can see we've been given a set of numbers over here. And this time we've been given some information about the sum of x, which means what happens if I add up all of these numbers, and the sum of x squared, which is what happens if I square all these numbers and then add them up. So that's what we've been given. And the first part of the question would like us to find the mean and the standard deviation. So this is actually just following on from the stuff we've done in chapter 2 before. So this was actually quite simple. So to find the mean, we quite simply have to do the sum of x divided by n. So we already know the sum of x, that's 148. And how many numbers do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. So we do 148 divided by 12. So if we put that into our calculator, that gives us a value of 12.3 recurring. So we'll just write 12.333 for now. And then the standard deviation, we also just follow the usual thing that we did. So we find the variance first and we square root it. So the equation for our variance was the sum of x squared divided by n, subtract the mean squared, or if you prefer to write, I could have just written this thing here squared, but it's the same as the mean squared. And that will give us the variance. So if you do that, we put 2362 divided by 12 minus 12.333 all squared. Or actually, just for the sake of accuracy, let's actually write that as 148 over 12 all squared. Rather than use that, I'll just use the fractional form of that. But anyways, putting that into our calculator, we get 2362 divided by 12 minus 148 over 12 squared. That gives you 44.72. So that's what our variance there for your standard deviation is, the square root of that. So if I were to square root the answer, we get 6.69. So that's going to be your standard deviation. So that part of the question is quite simple. So the next part of the question says, an outlier is plus or minus 2 standard deviations from the mean. So this one's actually easier to understand. So this one's actually using the equations we learned before, but it's giving us a new way of finding the outlier. So all you have to do is just pretty much follow this. So 2 standard deviations away from the mean. Well, the mean is 12.33. Let's say that. If I add on 2 lots of the standard deviation, so the standard deviation was 6.69, so 2 lots of 6.69, that will give me the upper bound. And let's just move that into the center. And if I did 12.33 minus 2 lots of 6.69, that would give you the lower bound of your thing, just according to what the questions told me. So for part A, you do that. This is what you do for part B. 12.33 plus 2 lots of 6.69 gives us a total of 25.71. And 12.33 minus that gives us a total of minus 1.05. So anything which is more than this would be an outlier. Anything less than that would be an outlier. So let's compare that to our data. So again, in the lower bound, there's nothing which is less than minus 1.05. So everything here is okay. But as you can see, this value of 30 is more than 25.71. So all of these values are fine. But then since our upper bound is 25.71, anything more than that is bad. So you can see here that 30 is more than that. So 30 is considered to be an outlier. And that's pretty much all there is to it. So when it comes to outlier questions, it's usually quite simple. It's either you find the mean, the standard deviation, and you do this kind of way, or you have something like the previous question where you use interquartile range and just use the equation that you learned before. And normally we're given a list of numbers or some data that you can use to find it. And it's pretty much as simple as that. So hopefully there wasn't anything too hard there. And let's take a look at the next part in this chapter. Okay, so now we've moved on to box plots, and box plots is something that people are quite used to from GCSEs. So I'll just go over the basics. There's not too much to actually go over for box plots. In general, when you draw a box plot, you'll have some piece of graph paper, and you'll tend to just have to draw, if we just draw out a random box plot, it'll look something like this, something like that. And then these different lines will, there'll be different sizes. So this might be further out, this might have been in the middle, this could be further out, and so on. But this is generally what your box plot looks like. And you usually have some sort of scale down here. So this might be something like 0, 10, 20, 30, 40, and so on. And then you can just read off the different values of what you're looking for based on the box plot. So what do the different lines actually mean? So basically, when you're doing this here, this is considered your lowest value. That's this line here. This one here is considered your Q1, otherwise known as your lower quartile. This middle line here is Q2, otherwise known as a median. And this one here is just Q3, which is the upper quartile. And then you can probably guess that this one over here is just the highest value in your data set. And that's it. So if you had to draw a box plot, all you had to do was find out what each of these are, and then just literally draw the lines on the graph, and then you just join them up like that. So anything between Q1 and Q3 you have to draw as a box. Once you've drawn the box, just draw the median inside it, then draw your two highest and lowest values, and then just join them up with a line like that. And that's pretty much all you have to do for that. If you were to have an outlier, the way you'd represent that on these graphs would be something like an X outside, and then this over here would be an outlier. And likewise, you could also have it on this side. So basically, this is kind of how you can represent your data. And that's pretty much it, actually. And normally you can compare different sets of data with different box plots. So if I just gave an example of what I meant by that is, let's say comparing to that, I had another box plot, which was something like this. Let's say this is the other box plot I had to compare. Normally when they ask you questions about comparison of box plots, what you tend to say is you want to talk about the medians and how they compare, and then you want to talk about interquartile ranges and how they compare. So normally if I had to compare, like, let's say I call this A, I call that B, what I would say is A has a higher median than B. So if these were like the heights of boys and girls in a class, let's say that A is boys and B is girls, and I say the median height of boys is higher than the median height of girls, which shows that generally they're taller than them. However, the interquartile range of boys is much higher than the interquartile range of the girls. Hence, the spread of heights of the boys is much higher than the spread of heights of the girls. Something like that. So that's kind of how you compare two sets of box plots usually. But before that, let's just see if you had a question like this, how would you draw your box plots and how would you do questions on here? These ones are quite simple, so there's nothing too much to do. So basically, when you have a question like this one over here, then all you need to do is you take your data set. So normally you won't get it like this. What will happen is you might have like a set of numbers like this again, like 1, 5, 4, 6, blah, 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 like, and so on. And based on all of that, what you should do is just use all the normal stuff to actually find this stuff here. So find the lower quartile, upper quartile, and stuff like that. But let's just assume in this question that you've already found all of that from your data set and you've got all of these. Then quite simply, all you really need to do is, to be honest, you just draw this on your graph. But I think the best way to do this would be, let's actually draw it to scale somewhat. So let's say every 2 is equal to 5. So 1, 2, 3, 4, 5. Let's draw an extra bit on for that. So let's say it starts from 0, 1, 2, 3, 4, 5, and 6. So we know our lower quartile is 3.5. So our lower quartile would be somewhere here. We know our upper quartile is 4.9, which is somewhere here. So we can draw that box. So we've done that. We've done that. We know the median's 4.1, which is somewhere there. And we can take that off. The lowest value is 1.5, somewhere over here, and the highest is 5.1, which is somewhere over here. And then you just connect those up. And there you go. You have your box plot. Now, let's say I had some values these came from, right? So this won't be the exact values they came from, but let's say they came from like 2, let's say from like 2, 3, 6, 7, 10, like 1. Let's just say some random values from that. It's not, these values won't match up with these numbers, but just to make an example. So it says an outlier is 1.5 times the interquartile range from Q1 to Q3. So the interquartile range for this question is just Q3 minus Q1, which is just 4.9 minus 3.5, which is 1.4. So my outliers should be 1.4 plus 1.5 times, the interquartile range. That should be, what's my lower quartile? It's 3.5. Take away 1.4, which is interquartile range, times 1.5, which is my K value. And my upper quartile is 4.9, so plus 1.4 times 1.5. And these two will give me my different ranges which are allowed. So 3.5 minus 1.4 times 1.5 is 1.4. And if I do 4.9 plus that, get 7. So anything which is less than 1.4 is bad, and anything which is more than 7 is bad. So if it happened to come from this data set, this is less than 1.4, so on this side this is bad, as that's an outlier. Anything which is more than 7, so 7's okay, it's on the dot, but then 10 is too high. So these are the two outliers in the data set, if that's where these numbers came from. And that's pretty much how you answer these kinds of questions over there. And that's pretty much it. So box plots are usually quite easy to understand. And normally what happens is when you draw the box plot, they'll give you another box plot and be like, can you compare the two? In which case you'll just do what we talked about here. You'll compare the medians and say this median is bigger or smaller, or larger and fewer. And then you have the two interquartile ranges which you compare, and that is pretty much all you need to know for box plots. So moving on from box plots now, let's take a look at cumulative frequency. So cumulative frequency is another thing that you'll be used to from GCSEs, and it's just something that you kind of have to get used to. So let's say you got a question like this, and you can use cumulative frequencies basically to estimate your mean and estimate the quartiles from your graph. So let's say I give you this kind of graph, and I say, look, I want you to draw the cumulative frequency diagram from here, and then let's estimate what the median heights are and what the upper quartile and the lower quartiles are. So the way you do cumulative frequency is you take your graph and then you add another column to it. So you see you have frequency, it's called the cumulative frequency. And all you do is you say, I started with 5, then onto 5 I add 12, so 5 plus 12 is 17. And what I did was I added that to that, then I add that to that, that to that, and that to that. So what happens if I add that to 8? I get 25. Then I do 25 plus 2, get 27. And then add on to that, I've got 32. So you can see my cumulative frequency graph has given me a total number of 32. So that means that everything in here adds up to 32. So you can just double check that. 5 plus 12 is 17. 17 plus 8 is 25, plus 2 is 27, plus 5 is 32. So that's all you need to do for the cumulative frequency graph. Once you've done that, and this won't be quite to scale, but just be roughly, you draw out your graph, like so, something like that, let's say. And then what you want to do is plot these onto your cumulative frequency. So this will be known as the cumulative frequency in the y-axis. And let's say this is the height on this side. So then what you would do is, let's actually do this somewhat to scale. So let's say this is 0, 4, 8, 12, 16, something like that. Normally you'll want to draw it to like much more accuracy. So you might want to go 0, 2, 4, 6, etc. But for this question, we'll just do that. And then what you'll say is, where does the lowest class start? So lowest class starts here at 4. So we start off at 4 for our graph. So I'll put in a thing here at 4. Then I know that the next one that I've got, this one at 4 starts here, but when it goes to 6, the cumulative frequency is 5. So let's just draw on the axis here as well. So this is 5, 10, 15, 20, 25, 30, 35. So when it goes to 6, we know it's, or the first class ends at 5. So I can draw a point at 6, about at 5. Then I know from 6 to 8, it goes to 17. So when it's 8, it should be roughly at 17, which is somewhere there. Then at 10, I know it goes to 25. So at 10, it's 25. Then I know at 12, it goes to 27. So that's somewhere here. And then at 14, it goes to 32. So that would be somewhere over here. Once you drew these points in, you just want to connect them with some sort of smooth curve. So it's important that the curve that you have is smooth, but that's essentially all you need to do for your cumulative frequency graph. You have to just join it up. Don't join it up like some people do with like lines, and don't do like lines which join it up. So what I mean is, don't do this. That would be wrong. It has to be a smooth curve. So something like that would be okay for it. But make sure that it is a smoothish kind of curve that you're doing. So yeah, that's pretty much all you need to do for cumulative frequency there. And then you've got your cumulative frequency graph. Then if someone asks you to find the median, it's actually easy, because normally if you had to find the median, if you remember, normally we said you have to do total number of things plus 1 divided by 2. But that's because you're normally working with discrete data. When you're working continuous data, you quite simply don't have to add the 1, because continuous, you just divide straight by 2. And you say, well, the 16th value is my median. So you go to cumulative frequency, go to 16, wherever that is. Let's do that in a different color. You hit the graph wherever it is. You go down and you read that value, whatever that value there is, that's your median value. If I asked you to find the different quartiles that you've got, so let's say the lower quartile, that's just 32 divided by 4, 8th value. So on my graph here, find the 8th value here somewhere, hits it there, that's your Q1, that's your Q2. Same for Q3, it's just 3/4 of 3 times 32 over 4. So that cancels out to 8 times 3, which is the 24th value. So again, just go to here, 24th value, draw it down. And so this value here is your Q1, this one here is your Q2, and this one, whatever here, is your Q3. That's it. You just simply have to read off the diagram, and that's it. So if someone asks you how to find the quartiles, that's what you do. If you then have to find percentiles, it's also easy. If it's like the 90th percentile, I say 32 times 0.9 gives me whatever. That's that number that you have to do. So if I say like find me the 80th percentile, so I'll do what's 80% of 32. Oops, 80% of 32. That'll give me some sort of number. Based on whatever that number is, you can usually round to the nearest number and then just mark it from the graph, and then you can find different percentiles like that. But that's pretty much it for cumulative frequency. A lot of it is the same stuff as what you've probably done during your GCSE times, so there won't be anything too tricky there either. And then normally you can draw box plots from this too, because you found Q1, you found Q2, you found Q3. The lowest value is 4, the highest value is 14. So I mean, if I'll just do that here, actually, if I was doing a box plot, let's just draw a random one like that. Then in terms of what you'd mark the values at, this would be 4. This is whatever I found in my graph on Q1, Q2, Q3, and this would be 14. So I got the 4 from here, and I got the 14 from here. And the rest of these I found from my graph. So that's pretty much it. That is cumulative frequency in a nutshell, and the different kinds of questions you can get from that. So from there, we'll look at the last way that you can represent your data points, and that will be histograms. So those are the ones that people kind of get confused with every now and then, but they're pretty simple to do. So we'll just kind of go through how you can do that. So let's take a look at histograms next. Okay, cool. So let's take a look at histograms now. So the area is proportional to the frequency in histogram. So what that means is, in a histogram, what tends to happen is, when we're working with data, the class intervals might not be the same. So it might be something like some intervals like 25 to like 30, and then the next one might be 30 to like 50, and then the other could be like 50 to 100, something like that. So the class intervals aren't always the same. So in histograms, what you want to do is, if you have a bunch of squares like this, then what we say is the area is proportional to your frequency. So we care about the areas, we don't care about how high and stuff like that is. The area is a key thing we want to know. And when you graph them, you have the frequency density on this side, and on this side you tend to have whatever x values you have. So normally what we do is, on your histograms, to find the height of each of the bars, so the height of each bar is a frequency density, we have to use a formula which is known as the area of the bar, so area of the bar is equal to k times the frequency. Now the thing is, it's just easier to say that k is equal to 1 if you want to draw graphs. So k can be anything, but in A-levels it's just easier to take k is equal to 1. So if we assume k is 1, then we say the frequency density, and this is the equation you actually want to learn, the frequency density is the same as the frequency divided by the class width. So that's how you can figure out what frequency density is. You just take the frequency that you've got and you divide that by the class width. And once you've done that, then that's pretty much it. You can get started with drawing histograms. So the best way really to learn this topic would probably be to just do an example. But one thing you should understand before that is just that the area is proportional to the frequency. That's the key thing that we want to know. So let's take a look at an example next. And one thing before you actually carry on might be worth mentioning is if I had something like this for my histograms, then if you take the midpoint of each of these and you join them up with a line, then you can make something which is called a frequency polygon using this method. So we can also take a look at that when we actually draw the histogram from our example. So let's go next. Let's take a look at an example here. So here you can see you have a set of data, and this can be the time taken for people to finish a race, and these are the frequencies of how long each person took. So we're just going to draw a histogram, and from that histogram we want to estimate how many people took 18 to 25 minutes to run this. So let's start off by drawing this histogram. So like we said before in our histogram, that the key thing was the left hand side, or the y-axis I should say, is the frequency density, and that's frequency density, and this will be the frequency in terms of the time that people took to run. So that's the time in t. So before we even do that, we should probably construct a table. So we say something like the time taken to run was 10 to 15, 15 to 20, 20 to 30, and 30 to 50. Now to be technically correct, I should write it like this, not like this, but this is just for the working out, so I'm writing it like that. Then after that, we have the frequencies, 60, 54, 36, and 40. Once you've got that, all you need to do is write another one known as the class width. So the class width of this one is 5. And how did I get that? Just, that's class width of 5. The other one is also 5. This one is 10 because 30 minus 20 is 10. And then this one is 20. So we have different class widths, you can see here. And now we can actually find what the frequency densities are. And quite simply to the frequency density, like we said before, frequency density is equal to the frequency over the class width. So just using that formula, we can find what the different frequency densities are. So 60 divided by 5 here. So you look at that divided by that, gives you 12. 54 divided by 5 is 10.8, I imagine. And then 36 divided by 10 is just 3.6. 40 divided by 20 is just 2. So those are your frequency densities. And now you've got that, all you need to essentially do is you just need to plot that onto a graph. So if you go down here, and we'll do a graph again, roughly to scale. So let's draw a line over here. And in terms of our time, we went all the way to 50. So let's just keep going all the way down. So let's say 0, 5, 10, 15, 20, 25, 30, 35. Cool, we've gone a little bit off. So 40, 45, 50. Let's draw that there. This is the frequency density. This is the time t. Our frequency density only goes up to a maximum of about 10, actually 12. So let's just go up something like 2, 4, 6, 8, 10, 12. That fits in perfectly. And now let's just fill that in. So starting from the beginning, our first class doesn't actually start from 0, it starts from 10 to 15. So we're actually looking at something which is between 10 over here and 15. So that's where the first two are. And what is the frequency density? The frequency density of that is 12. So what we do is draw the bar over here. So this one here would look something like that. So now from 15 to 20 is 10.8. So that would be somewhere here. That's 15 to 20. Then 20 to 30 is 3.6. So 20 to 30 is somewhere over here. And 30 to 50 is just a small value of 2. So 30 to 50 is something like that. And that's it. That's all you have to do for your frequency densities. And this is how you drew a histogram. We actually have a histogram now. And like I mentioned before, if I were to join the middle parts of each of these, so this one is 30 to 50, so that's 40, that's the middle part, then I'll basically just get myself a frequency polygon. So what I mean by that is a line there, a line there, a line there. That essentially gives you your frequency polygon in terms of how you work with that. But that's it, you've drawn your histogram. Now the question was, based on that, how many people took between 18 to 25 minutes to do that? So how do we figure that out? So what we need to do first is, let's actually figure out in a different color. Let's do it in orange. Where exactly is 18 and 25 minutes on a graph? So 18 is somewhere here. 25 is, or 24 it was, 25 is here. So we said the area under the graph is representing the frequency, and here we're asking how many people, hence the frequency. So if I drew a line from here to here and here to here, this question is just asking me, what is the area of the shaded part of this histogram? That's what it wants me to know. So that's what I need to do. I need to find this area. So how do I actually do that? Well, I need to figure out the number of people in that, area that I'm using. So let's take a look at how we do that. So to figure that out, let's take a look at what classes this falls into. So just, I'll write that down here actually, so I don't forget, between 18 and 25 minutes. So where does 18 fall? So 18 falls into the class over here. And where does 25 fall? 25 falls into this class. So in this class, I've got 15 to 20 people, and 18 falls somewhere over here. So I need to extrapolate between this graph. So since 18 people falls between 15 to 20, I say that from 18 to 20, how much does that give you? Well, that's just 20 minus 18. So there's a gap of 2 to get from this 18 to the 20 people that you have. So you take 20 minus 18, and all you do is you times that by the frequency density of that class. So the frequency density of 15 to 20 is 10.8. That's what you do. Now, which class does 25 fall into? That falls into 20 to 30, and 25 is somewhere here. So how far is 25 from that? It's only 5 away, or otherwise 25 minus 20 away. And you times that by the frequency density of that class, which is 3.6. So as you can see, these two will give you some answers. So let's see what that gives you. So this one gives you 2 times 10.8, which is 21.6. And this one gives you 5 times 3.6. So 5 times 3.6 is just 18. So now that I've got 18, we can add up these numbers, 21.6 plus 18, giving us 39.6 as a value. So the estimate would be roughly 39.6 students, and you can say, if you round that up, is roughly 40 students is what you should have. But in terms of student-wise, or in terms of numbers, you can say that this is the answer of the estimate that we've given. Obviously, you can't have that many students, so actually it should be something like either 39 or 40. But that's how you figure it out. So what did we actually do? First, we figured out that this is the times we want to go in between. So which class does 18 fall into, and which class does 25 fall into? We found it fell into this class and this class. Then we want to say, if it's 18, well, this is 15 to 20, and 18 is like somewhere over here. So we need to find out how far 18 is from 20. And same for the other one, this is 25. How far is 25 from 20? So when you find out how far they are, so this is 20 minus 18, so it's 2. And this is 25 minus 20. You multiply with them by the respective frequency densities, and then you get your 2 answers, which you add up, and that gives you your final frequency. So I hope that wasn't too bad, and then we can go through some more examples in another video of how to do this kind of question. So once you've done that, there's another type of question you can expect. So this is a question that you can take a look at. So it's quite a bit to read, so let's go through it together. So it says, on a histogram, a rectangle represents the class 12 to 14. It's 4 centimeters high, 3 centimeters wide, and the frequency it represents is 36. And X is the mean number of days that it's cloudy. So let's say maybe the number of days is cloudy in a year. That's the mean number of days in a city. So what area is each day represented by? So just so you know what's happening is we have a rectangle from 12 to 14, which is 3 centimeters wide, and 4 centimeters high, and it represents a total frequency of 36. So the frequency it represents is 36. Now, this is a rectangle which is part of a whole histogram set. So this is actually what the whole thing might look like. And it's just talking about this one histogram square or rectangle that we've got here. So the first question is quite easy. It says, what area is each day represented by? And to do this, what you have to do first is you find the area of the bar, which is 3 times 4, which is equal to 12. And this area of 12 is representing 36 as a frequency. So you just say the area divided by the frequency is what you want. So the area divided by frequency is 36, or actually 36 on the area. The area is 12. And this area of 12 represents 36 people. So the frequency density is 1/3, or 0.33 centimeters squared. And that's what each day is represented by. That's what each day is represented by for the area. And then quite simply, it says the total area is 60. So if the total area is 60, then how many days are there in total? Well, for part B, we know that each day is represented by 0.33 centimeters squared. We have 60 centimeters squared. So quite simply, to find the total number of days, you just divide the two by each other. And I think what might be better is, since we know that actually it's 1/3, so let's stick to 1/3. So let's say 1/3 is the area for each day, and we have 60 in total. So 60 divided by 1/3 means that we have 180 days in total. And that's it. We know that there's 180 days in total. So these kind of questions are quite simple. If you just follow the area, figure out if you've got a total number of frequencies, then for that total number of frequency, all you have to do is do the area divided by the frequency, and it gives you what area is represented for each kind of day. And then if you have a total area, you can just divide it by that and get the total number of days. So this kind of question is quite simple to follow. And that's kind of it in terms of representation. The last thing we have in this chapter is just comparing two data sets, which we've already talked about, but we'll just really briefly recap what we said. So there's two things you can do. You can compare the measures of location. And we've already done this before because we talk about the interquartile range, or not that one, sorry. We talked about compare the median. So you talk about Q2, or you might talk about the mean in some questions. You might talk about stuff like that. You might talk about the mode or whatever. And then the other thing you're going to compare is a measure of spread. So that's another thing you want to put. So you might want to put in stuff like, the variance. You might want to talk about the standard deviation and so on. But these are the two things you want to compare. You want to compare a measure of location and a measure of spread. So normally when you have a question, you can either compare data using like mean and standard deviation. So usually a measure of location, the standard ones would be if you have the mean, you would then use a measure of spread, which is the standard deviation. Or if you have the other one, that would be where you look at the median. And if you have the median, you tend to compare that with the interquartile range as your measure of spread. So that's pretty much it. So if your data set has like extreme values, so it's like huge values, then the mean will be affected by that, like we talked about before. The mean is not good when you have extreme values. So in that case, when you have extreme values or outliers like that, you want to use the median and the interquartile range because that's better to use. So for questions like that, that's the stuff you have to keep in mind. So yeah, other comparisons might be stuff like the box plots we talked about. So we already talked about how you can compare the box plots, just compare the two different medians, compare the different interquartile ranges, and that tends to be it. So usually they'll get you to actually calculate the mean and the standard deviation or stuff like that before. And then once you've done it, they'll say, look, another data set has this mean and this standard deviation. And then you just say data set A has a lower or higher mean, and then it has a lower standard deviation. And you just compare that back to the question. So these questions are quite simple to do. And that's pretty much it. So I hope that this topic was okay. A lot of it does come from GCSEs. And yeah, pretty much that's all good. So if this was helpful for you, it'd be great if you could share this with your friends. The statistics set for year 1 is complete now. So if you follow through the entire playlist, you'll pretty much be able to catch up on everything in year 1 stats. And from now, we'll be carrying on with year 2 stats in the other videos. So I hope it's helpful. And as always, just if it is great, then just leave a comment below or subscribe, or just let your friends know, because the more people that watch it, I can make some more videos on other topics like pure and mechanics and further maths and so on. But I just want to make sure that it is helpful for everyone. So I'll see you in the next video in the next series.